You have an unfair advantage at the moment. How about this? Partial x of x to the y. Partial y of x to the y. How do those go? Now it's starting to get a little bit dicier, isn't it?
Y minus 1 x to the y minus 1.
So yes, indeed, we have y x to the y minus 1, because you can think of y as being like n. It's held constant. It's just a constant with respect to x. How about this one? It's just what? So this one is not. So this one would be, by analogy, I would say this is kind of like d dt of a to the t. So the base is x. It's being held constant with respect to y. So this is essentially like the derivative of an exponential function. So it's more like this is analogous to that, right? And you know how to differentiate this, right? Natural log of a times a to the t. So this becomes natural log of x times x to the y. So there's a little bit of a learning curve there in terms of just pattern recognition. Let's do another. How about partial x of, I don't know, inverse tangent of x squared plus y squared? What's the derivative of inverse tangent? You guys have had calculus 1, you know this.
1 over 1 plus x squared.
Or you've taken my calculus 2 test recently and you wish you knew this. Or you've taken Dr. Sprano's calculus 2 test recently and, well, I don't know what happened there, but it was rough. Yeah, I've seen it. I was like, that's a test. That's a nice test. Anyway, so 1 over 1 plus the variable squared, right? Times the derivative of the inside function, which is what? That, right? So what does this simplify this to? This simplifies to, yes, indeed, 2x over 1 plus quantity x squared plus y squared squared. All right, so we got that one. Now, sometimes you do something like this. And so what if I was to ask you, what's partial y of inverse tangent? X squared plus y squared. How would that go? If you've already done the x derivative and you understand, hey, there's a symmetry here between x and y, right? So I don't need to go through all that again. I can just say, okay, well, x and y have their roles reversed. So this is just going to work out to 2y, right? Over 1 plus quantity x squared plus y squared. So you can do that. Let me do a couple of partial derivatives which will be relevant to our future theoretical purposes, all right? So these are calculations of note. But I think it's also good practice with partial differentiation. Suppose you want to let r equal to the square root of x squared plus y squared plus z squared. So this would be the so-called spherical radius. In math, we tend to use a rho for this because, I don't know, that's just happened in calculus books. But in physics, almost universally, we use r for the spherical radius. And we tend to use s for the polar coordinates radius. But anyway, what is partial r partial x? How does that work out? We differentiate the square root function, right? So we go 1 over twice the square root, x squared plus y squared plus z squared, yeah? And then what? Then partial x of the inside function, chain rule, yeah? So how does that work out? Yeah, that's 2x. And can you recognize what the other is? Like we can rewrite that in terms of r again, right? So you've got a 2 and a 2, and so what you end up with is just x over r. That simplifies back down to x over r. So how about, if you understand this, what's partial r partial y, you think? Same calculation, but y over r, right? And partial r partial z would likewise be z over r. Okay. So I have additional examples in the notes for you to look at, but this is basically it. If you can differentiate, you can partial differentiate. Nothing to be scared of. You just differentiate and assume that the other variables are constant. Yeah.
Are you allowed to tell us what this is like used for?
Oh yes, we're getting there. So like I said, detour. So next up, we put these together. We put these together. And we make something called the gradient. What's the gradient? Well, let me define it for you. So if we have a function of 2 or 3 variables, definition, if you have f, I'll write 2 definitions if you guys don't mind. We could have f as a function of x and y, or we could have f as a function of x, y, and z, all right? So either a 2-dimensional or a 3-dimensional context, all right? In the 2-dimensional context, the gradient of f is just equal to partial f, partial x, partial f, partial y. In the 3-dimensional context, the gradient of f is a 3-dimensional vector, partial f, partial x, partial f, partial y, partial f, partial z. These are both called gradient of f. So the gradient, what does it do? It takes in a function, a scalar function, and it outputs a vector. Yes?
Did we use a gradient within the context of this course?
Yes. Yes. I only go over things in lecture that we're going to actually use in the context of this course. So, for example, the homework which is due next week has this stuff in it, but not all of it, of course. But okay, so these are gradients. What is the point? Well, the point is this. There is a fundamental theorem of calculus, FTC for line integrals, and it says the following. It says that the integral of the dot product of the gradient of a function, so basically the line integral, if you will, if you calculate the integral using the definition I wrote at the start of class of the gradient of a function, all right? And so here I'm talking about a curve which goes from, say, point P over here to point Q, like that. What do you think the answer would be? Sorry. That keeps hooking me. Oh, you already got me. Never mind. Any ideas? What does the fundamental theorem of calculus part 2 say? Do you guys remember? I mean, you know this, right? If you've got df dx, what's it equal to? F of b minus f of a, right? We all know this. This is also true for the gradient. So this is equal to f of q minus f of p. Now here p and q are points in either 2 or 3 dimensions. All right? So let me put it all together for you. There are special forces, there are special forces which can be written as the gradient of a potential function. Let me make a definition. Oh man. So definition, F is a conservative force if F is equal to minus the gradient of U. So here, the reason for the minus will become apparent soon enough. And this U is, you might call another, you could have a clumsier notation for it. U often we'll call the potential energy. So U is the potential energy function. So, all right, let's put this all together. Suppose you have the situation that your net force is a conservative force. What happens then? What happens if your net force is a conservative force? So if your net force is a conservative force, if your net force is a conservative force, then we could calculate the work done, right? The work would be the integral over the curve in question, right, of f dot dr. But there are two ways we could go here. The one way we could go would be the work-energy theorem. The work-energy theorem says that that integral is the change in the kinetic energy, right? So on the one hand, by our previous calculation today, this is the change in the kinetic energy, right? The change in the kinetic energy. But what else is it? Well, it's also equal to minus the integral of the gradient of u dot dr, all right? And so by the fundamental theorem of calculus for line integrals, that is equal to what? Well, that's equal to minus u of the ending point minus u of the starting point. So here I'm assuming that the curve goes from like 0.1, you know, 0.1 here over here to, let's say, 0.2 for the sake of this discussion down here. And what are you looking at then? Well, look at it. You've got, if I use, I'm going to use kinetic energy equals to k for the sake of shortening the what I'm writing here. So that's equal to k2 minus k1. And so what has happened here is you can solve, right? You can rearrange it so all the 1s are on one side, all the 2s are on the other side. And what you have then is you have k1 plus u1 equals to k2 plus u2. So will we use this in this course? Oh yeah, we will use this in this course, because what I'm writing here is exactly the conservation of total mechanical energy. If your net force is conservative, then the total energy is conserved under the motion. So that's, you know, you started asking me, why are we doing this? Why are we interested in it? We're interested in it because if the force is conservative, then we can understand the motion by just analyzing energy being equal before and after a process, which is very, very useful. It makes problems that we've been solving in more complicated ways much easier. So, but anyway, at the base of things here for us at the moment, to understand better, of course, we'd like to understand better, like, when is a force conservative, right? So I'll have to, you know, I'm not going to try to do all that today. We'll talk more about this another day, of course. But any questions before I go on here? So we'll apply this. I mean, I can tell you one thing. No, I really just should stop here. This is a good place to stop in terms of the theory. That's why we care about partial differentiation. One example. So example 9. I'll make it pretty simple. Suppose your force is like, oh, I don't know, x comma y squared. Is that a conservative force? Is this force conservative? What would you have to do to figure that out? You would want for this to be what? You would want for f to be equal to partial f partial x, partial f partial y, right? So you have to do some basically anti-differentiation there, right? So I need this to be that, right? And I need this guy to be that guy. So I suggest that means f is equal to, oh, I don't know, 1/2 x squared plus 1/3 y cubed. That is a potential in the sense of calculus 3. What would the potential energy be for this function? What would we want for potential energy? So I'd write u is minus 1/2 x squared minus 1/3 y cubed. This would be the potential energy function for that force field. Because if I take the gradient of that and multiply by -1, I get the force back again. See, you can calculate the gradient of this u with a minus is equal to f. And then if I wanted to calculate the work done by this force over some path, I could calculate it using the potential very easily. As well, I'll show you in detail like next class. But anyway, I think that's a good place to stop. Listen, this is the theoretical backdrop, so we will be much more like planes and pulleys and stuff like that like next time, okay? But I do need to set the stage here, and that's what we're doing today. So sorry if it was a little bit scary.